Hi everyone. Thank you for coming to this ITC Colloquium. I'm very pleased to introduce Louise Edwards. Louise is an expert on brightest cluster galaxies, which are intrinsically interesting because they're some of the biggest objects in the universe, but also interesting because of how much they tell us about galaxy formation and our cosmological models. And so Louise is an absolute expert in this area and also an expert in getting work out of undergrads, which I'm not sure how many of you have tried, but it takes a lot of intelligence to do that well. Louise has been, you hear the drilling's coming back, Mark? Never mind. It sounded like they were starting to drill again.
You look beautiful.
Okay. Louise has been at a number of different institutions, including Caltech for a postdoc. Many of the people in this audience know her as a professor at Yale. She's now a professor at Cal Poly, where she is joining us from today. Louise is Canadian, and I don't have a really good picture of this, so you're going to have to just trust me. But one of her many claims to fame, in addition to being an expert in brightest cluster galaxies, is she's on a Canadian postage stamp. I encourage you to look it up. But we're very fortunate to have her here today, so let's give her a warm welcome.
All right, so brightest cluster galaxies, old stars, old stellar population, high metallicity population in the core. Ages stay pretty high up until about 1 times the effective radius. Well, we notice a gradient, negative gradient in metallicities. When we look at the velocity dispersion, again, right at 1 RE, right, 1 effective radius, we start to notice a difference, a signature, that something, some new population, some different population is happening past 1 RE. On the outskirts of the brightest cluster galaxy, the BCG, coming into the ICL, the intracluster light. So this is work with mostly undergrads, as Eric was saying. Undergrads from my time at Yale as a lecturer, and also from my current job at Cal Poly, in addition to our lovely co-authors here. Grant included is on this project. On the ground, we tied postcards to balloons for peace. Prince Charles married Lady Di, Rock Hudson died. We learned new words for things, the decade changed. The first few pictures came back blurred, and I felt ashamed for all the cheerful engineers my father and his tribe. The second time the optics jibed, and we saw the edge of all there is. So beautiful and alive, it seemed to comprehend us back. You know what they're talking about? Hubble Space Telescope, yeah. So Tracy Smith's father was an engineer who worked on the Hubble Space Telescope. And nice picture to open up here, some brightest cluster galaxies in one of the Frontiers Fields clusters. A little bit higher redshift than what we're talking about today. Today we're talking about a sample of low redshift, so local brightest cluster galaxies. Let's take Abell 85. Abell 85, it has no bound close companions. It's smooth galaxy in the optical. In the X-ray, it's very smooth as well. The intercluster light and the brightest cluster galaxy stellar populations differ quite a bit. The center and the outskirts of the BCG are here. The ICL is way over here. This is metallicity. This is age. There's been plenty of time for the infalling galaxies far from the core to collect in on the ICL. Another galaxy, Abell 2457. I'm not going to go through all 23, by the way, in this sample, just 3. Abell 2457, one potential minor merger, the tiny little galaxy in the southwest. This galaxy cluster is smooth in the galaxy is smooth in the optical, but in the X-ray there's substructure that we can see. There's a smoother change in stellar properties from the BCG to the ICL. So for example, the companion bridges the gap between the stellar populations of the core and the ICL. This low mass close companion has the youngest stages and the lowest metallicities, if you look in detail, that are between that of the BCG and the ICL. At this stage, minor mergers are building the BCG and contributing to the ICL. Final one, IIZW 108. Currently, this system is undergoing major mergers. It's in the process of building its BCG. There's little extended ICL, and the ICL that does have has a population of young metal poor stars that actually don't exist in the other galaxies. These major mergers are not going to contribute to like a young metal poor component of the ICL, but part of this population will age over time and will probably contribute to an old metal poor component. That's something that's common that we see in the ICL of our sample. Okay. Mm-hmm.
Is there a coincidence that the uncertainty of the age of the emerging subcomponent in 2457 sort of extends from the age of the ICL?
Oh yeah, totally. Yes, it is. It's a pretty uncertain result. Yes. I'll show some spectra in a little while. We stack our spectra. We get up to a signal to noise of on the outskirts, and in some of these companions, you know, sometimes we're dealing with like a signal to noise of 10. Usually it's higher, but sometimes it's 10. So it's a low signal. Okay, so why study BCGs? Brightest Cluster Galaxies might be a local analog of galaxy buildup at high redshift, as Erica was kind of alluding to earlier. So a knowledge of feedback and minor and major merging is certainly important. BCGs are associated with the cluster as a whole. So the interaction between the AGN and the effective cluster cooling, very interesting to know about. A knowledge of activity of the cool core cluster, BCGs in particular is important, and line emissions, stuff like that. The outskirts of the BCG and the intercluster light are a fossil record of galaxy dynamics that have happened in the cluster. So a knowledge of the BCG plus ICL may be an important dark matter tracer as well. And finally, BCGs can act as a powerful constraint for cosmological models, as matching stellar and gas mass, metallicity and alpha enhancement are always difficult. So a knowledge of stellar formation history is also important. So the main question that we're going to talk about here is a clock right there, is how closely connected is the building of stellar mass in the BCG and the ICL. So we're going to explore galaxy kinematics and stellar population ages and metallicities, and hopefully this will help. Okay, so today's models and simulations do a very good job, have done a very good job of being able to make massive galaxies that are not subject to overcooling problems, that are roughly the right color with accurate stellar ages, but are still limited in their ability to model large-scale physics, like the cosmic web, with small-scale physics, like feedback with the AGN. In different codes, different implementations are used in terms of feedback, anything from thermal heating to jet heating to just shutting off star formation, you'll find in different codes. One area in today's simulation that still needs to be addressed is this inability to match, for the most massive galaxies, the number and luminosity of those galaxies. So for example, these models are a little bit old, but if you look at the GWO 2011 models, for the most massive galaxy, we are counting too many galaxies compared to what is observed. Also, we are counting too much stellar mass at z equals 0. So here's redshift, here's stellar mass, here are the models in the green triangles, and the galaxies have too much stellar mass. You can also see this here with the Tononi models as well, and the observations in dots with the BCG stellar mass and the look-back time. Finally, we often see too much recent star formation, or star formation that is too bright. Or if you can match them, then you end up blowing out too much mass, or too much mass from the galaxies, something that more than what we see observationally. Looking at simulations that talk about the ICL, the intracluster light specifically, the Morante simulations of 2007 suggest that 75% of the ICL stars come from progenitors of large red galaxies, okay? So mergers and interactions with the large red galaxies, the removal of those stars is what falls into the cluster core and makes the ICL. So they see that the fraction of these are ICL stars, is highest for the most massive galaxies, right? That's where all the stars come from. However, on the other hand, other models that look at the ICL, like those of Martel and Contini, suggest that most of the ICL luminosity instead comes from L star galaxies. So that's really different there. Is the ICL coming from LRGs, large red galaxies, or from L star galaxies? We can critique the observations, of course, as well, right? We need more stuff observationally. To get a spectrum of the ICL is really hard, because it's very faint. And up until recently, there's only been a few really good spectra, and they haven't necessarily matched. So I'm showing, for example, a spectrum from Melnick from 2012 that shows that the best fit to their ICL spectrum is old stars that are metal poor or have solar metallicities. But this is in contrast to some other spectra that are out there for Coma and Hydra, which show metal-rich populations. Oh, I think I did that the wrong way, sorry. This one is metal-rich, the others are metal-poor. In terms of kinematics that you might get from a spectrum as well, the velocity dispersion is shown to both rise sometimes. So if you look at the velocity dispersion of the stars from the core of the BCG to the outskirts to the ICL, sometimes you see that rise, sometimes you see that fall. This is some really nice work from Loubser from last year. Their spectra go out to 1 effective radius, so they're going into the outskirts of the BCG, but not really into the ICL. Nonetheless, for some of their most massive galaxies, they're finding rising velocity dispersion.